Hello. In this video, we're going to take a look at an LTSPice simulation of the basic BJT current mirror. I have my BJT basic current mirror. Let's say I wanted to design it for a reference current of about 1 milliamp from a supply of 10 volts. And that means since my reference current is going to be equal to VCC minus VBE, divided by R, if I want my reference current to be 1 milliamp, that means my resistor R will be VCC minus VBE over IREF, which in this case is 10 minus, let's assume 0.7 volts for the VBE drop, divided by 1 milli, or 9.3 kilo ohms. With that, since this is the basic mirror, I know my output resistance, which is resistance looking into the output of the current mirror, which is essentially the collector terminal of Q2. It's going to be approximately equal to little out 2, which is the early voltage divided by the quiescent collector current of transistor 2. And if we assume an early voltage of 100 volts, this is going to be 100 divided by 1 milli, or approximately 1 milli, so approximately 100 kilo ohms. So that's what I expect for my output resistance. Now let's take a look at the simulation and see if that matches, if the simulations match our expectations. I've designed the basic mirror. In this case, I have modeled my transistors because normally we will be using current mirrors with integrated circuit design, and so it's going to be much more typical to work with models as opposed to working with off-the-shelf transistors. I made a simple model. I've only modeled 3 parameters: the saturation current, which in this case is 10 to the 10 times 10 to the minus 15 amps. The early voltage is 100 volts, and beta of the transistor as 100, the current gain. Let's go ahead and run my simulation. Here is my R resistor, and my VCC is equal to 10 volts. So I'm running my simulation. Notice that I have placed a voltage source in series with the output, and then I am performing a DC sweep to sweep that voltage source from 0 to 10 volts at the steps of 0.1. And the reason why I'm doing that is because it's going to give me an idea of different loading conditions, and then I can also measure the compliance of my current source as well as my output resistance. So I'm going to go ahead and measure the current. I'm expecting my output current to be around 1 milliamp. And there it is for different values of voltage. Notice that as my voltage becomes very low, my transistor goes into saturation, and therefore my current drops quickly to 0 as the transistor eventually cuts off. But within the linear range of the transistor Q2, my current is approximately equal to 1 milliamp, and it increases slightly with changes in loading conditions, which is just an indication that the output resistance of my current source is not infinity, which will be the ideal value. And the output resistance obviously comes in units of voltage over current, and this graph will have output current in the y-axis and output voltage on the x-axis. So the slope of this line will actually have units of current over voltage, so the output resistance will actually be the inverse of that slope. Let's go ahead and measure it. So I can do that using my cursors. I can move this out of the way. Put my first horizontal cursor, sitting at around 5 volts. And I'm going to move it to around 1 volt and measure my current there, and then I'm going to put another cursor, my cursor 2, going to put it at 10 volts, and that's going to give me a 9 volt delta. I'll measure the delta in voltage as well as the delta in current, and the delta in current over the delta in voltage is going to be this slope over here, and my output resistance will be the inverse of that slope. And if you calculate that inverse, you can see that it's going to be approximately equal to 100 kilo ohms. That is what I expect for my little arrow for my transistor from the calculation. So let's go ahead and say, I'm going to enter some text and just say my output resistance is equal to 1 over the slope, which in this case is 1 over 9.8, 5, and 5 e to the minus 6. We don't really need those many digits, so I'm just going to carry it at 9.85, I think, to make it more readable, and that's approximately equal to 100 kilo ohms. All right, and that will be the output resistance for my basic current mirror. My compliance is going to be the range of loading conditions for which the current remains constant. And I can see that I am within compliance. Normally we're going to count up to the point where the output current drops by, it depends on the specification, it depends how accurate you want your current source to be, but you could measure it, for example, when it drops by 5% of the nominal value. And so you will see that it's actually something very close to zero. It's going to be probably 0.3 or around that, around the saturation voltage of the transistor. Because that's essentially what we have, a single transistor in that output node. And therefore, the only thing that you need in terms of voltage is just sufficient voltage to keep Q2 out of saturation. That's it. We're going to look now at other current mirror configurations and compare it to the basic mirror. Thank you. Hello. We're going to take a look now at the base-compensated current mirror, sometimes referred to as the 3-transistor current mirror, where we've basically taken a basic mirror and we have added that beta helper transistor Q3. Now, we mentioned previously that if we just leave the configuration like this, Q3 is going to have a collector current that is comparable to the base currents of Q1 and Q2. And therefore, if we want to get full advantage of the beta helper effect, which will give us more accuracy in our output current or a better current transfer ratio, then we'll need to make the collector current of Q3 comparable to the collector currents of Q1 and Q2. We can do that by adding a biasing resistor. I'm going to call it RB for biasing resistor, and the purpose of that resistor is simply to increase the collector current of Q3 to a value comparable to the current through Q1 and Q2. Notice that in this case, I have 2 VVE drops from ground to the lower terminal of resistor R, the reference resistor, and therefore my expression for IREF is going to be equal to VCC minus 2 VVE divided by R. Now imagine that I want my IREF to be equal to 1 milliamp, just as I did before. Then my resistor R is going to be equal to VCC minus 2 VVE divided by IREF, or 10 minus, let's assume VVE is 0.7 volts, so minus 2 VVE will be minus 1.4 volts divided by 1 milli. So this will be 8.6 kilo ohms. And that always gives us 1 milliamp flowing through transistor Q1, approximately 1 milliamp flowing through transistor Q2 as well. If I wanted to have the same level of current flowing through transistor Q3, notice that I will need to select my RV resistor to have the particular value to give me a current of approximately 1 milliamp. In order to do that, I know that the voltage across transistor RV, resistor RV, by design is going to be 1 BBE drop. So my RV must be equal to VBE divided by IV. IV being, of course, the current through that resistor. Not to be confused with the base currents, so perhaps I will rename it to IRB. Okay, and so this is 0.7 volts, and I want my IRB to be approximately 1 milliamp. So this will give me 700 ohms. My output resistance will still be approximately equal to little arrow for my transistor Q2. And so that's going to be VA divided by the collector current of Q2, which is I out, or 100 divided by 1 milli, which is around 100 kilo ohms. Let's go ahead and run the simulation to verify this result. I'm expecting also my compliance range to be similar to that of the basic mirror, because I still have only one transistor at the output that I need to keep out of saturation, that's Q2, and so this voltage should be able to be dropped all the way down to 1 saturation voltage. Let's take a look. And I can see my 1 milliamp there. Go ahead and turn on the grid so we can see better. So I can see that 1 milliamp increasing slightly with increases in the load, and so that means that we have some output resistance that is finite, as we expect. And I'm gonna go ahead now and turn on my cursors, as I did before, and try to measure maybe from 1 volt, 4 to 10 volts. And my slope is now 9.95 e to the minus 6. And still the inverse of that slope will be approximately equal to 100 kilo ohms. So I can write again my R out equal to 1 over the slope of this line is equal to 1 over 9.95 e to the minus 6, approximately equal to 100 kilo ohms. And that's it for the base compensated current mirror. Thank you. Hello. We're going to take a look now at the simulation for the emitter-degenerated current mirror. And so we have taken our basic current mirror and we have added resistors R1 and R2 in series with the emitters of Q1 and Q2. We had studied that the relationship between I out and I ref will then be proportional to the ratio of R1 to R2. Let's imagine that we want to run our current mirror from the same supply as before, 10 volts, and for the sake of example, let's assume that we want our output current or reference current to be equal to 1 milliamp. Notice that now the voltage drop that I will have from the lower end of resistor R to ground, it's going to be 1 VBE plus the voltage drop across resistor R1. which we can refer to as VR1 perhaps. And I can assign that whatever I want it to be, but notice that the higher that voltage, well, I guess it depends on the ratios that I have chosen for R1 and R2, but typically the higher that voltage, the lower my output compliance range will be, because I will need my output voltage to be equal to one saturation voltage for Q2 plus whatever voltage drop I need across resistor R2. Let's imagine that I want to allocate 1 volt to be dropped across R1, and for the sake of a simple example, let's assume that I want both Iref and Iout to be equal currents. So in that case, I want the R1 to be equal to 1 volt, which means R1 will be equal to 1 volt divided by 1 milliamp or 1 kilo ohm. And let's assume, instead of want, I'm going to say choose. And assume we want Iout to be equal to Iref. In that case, R2 will also be equal to 1 kilo ohm. So the ratios will be, or the resistors will be equal to each other, so that the ratio will be equal to 1. With that, I can now calculate my Iref, which is the current flowing through resistor R, as VCC minus VBE minus VR1 divided by R. If I want Iref to be equal to 1 milliamp, then in that case my R is going to be equal to VCC minus VBE minus VR1 divided by Iref, or 10 minus 1.7 divided by 1 milli. Which is going to be equal to 8.3 kilo ohms. And therefore, I'll have 8.3 kilo ohms for resistor R, 1 kilo ohm for each one, R1 and R2. And that's what I have here in my simulations, or in my circuit schematic. I can run my simulation really quick, and I can plot my current across resistor Q2, which, as expected, is going to be equal to R1. Notice how, since I now have 1 volt across that resistor R2, my compliance has decreased, since I now need at least 1 volt plus the saturation voltage of Q2 at the output in order for the transistor to be operating in the linear region and the current source to be operating properly. Therefore, my compliance range has decreased. I can still go ahead and measure my output resistance. And it's really difficult to see really a slope here, but if we use the cursors, we're going to see how the output resistance is not exactly equal to 0. Of course, we haven't done the calculations on this, so let me go ahead and do those. But we are expecting, in this case, the output resistance is going to be equal to, I'm going to write my assumptions as I did before. So assuming my early voltage is equal to 100 volts, my beta is equal to 100. My output resistance are out. Looking into the collector of Q2 is, now that I have added that emitter resistor, going to be equal to little rho 2, 1 plus GM R pi 2 in parallel with R2. Okay, and I need to calculate little rho 2 for one thing. It's going to be VA divided by IC2, or approximately 100 volts divided by 1 milli, or 100K. My GM is going to be equal to the quiescent collector current, IC, 2 divided by the thermal voltage, which at room temperature is going to be around 25 millivolts. And so this is going to be 1 milli divided by 25 milli, which is 0.04 amps per volt, or inverse unit of ohm. We will also have expressed it as ohm to the minus 1. R pi 2 is going to be beta times little r2, or beta divided by gm2, which we have already calculated. But let's go ahead and recalculate that way. So 100 times 25 milli, little r2 obviously is going to be thermal voltage divided by quiescent collector current. So 25 millivolts for the thermal voltage divided by 1 milliamp. And that's going to be 2.5 kilo ohms. And R2 is just going to be 1 kilo ohms. So if I do my calculation, I'm expecting this to be little r, also 100k times 1 plus 0.04 times 2.5k in parallel with 1k. And that's going to give me something in the order of 2.5 mega ohms. I think it's 2.9 mega ohms in this case. So let's go ahead and run my simulation, see if I come close to that. I'll touch my cursor. In this case, I'm going to run it from 2 volts instead of 1, just because at 1 volt I can see that I'm out of compliance. So I'm going to run it from 2 volts all the way to, take the other cursor, all the way to, oops, that's the original cursor. Try this again, so 2 volts. There. Sitting at 5. And it doesn't want to pick up the second cursor. I guess maybe I'm just clicking. Okay, it turns it on. Oh. Can I just put it where I want? Of course not. Right around 2. Close enough. Okay, let's make this guy down to 2. Oh, now it's picking it. Okay, so 10 volts, close enough. And I get, for my slope, 4.03 e to the minus 7. So we can see with the slope has decreased by an order of magnitude, factor of 10, because before we had something e to the minus 6. If we do the calculation, we can write our output resistance in this case as it being equal to 1 over the slope, or 1 over 4.04 e to the minus 7. Which gives me around 2.5 mega ohms. So we can see we have improved the output resistance with respect to the basic mirror, which used to be 100 kilo ohms. Now we have 2.5 mega ohms. And the other thing I wanted to show is how the currents are going to vary by varying the ratios of the 2 resistors. And so we can just do one quick, if I wanted, for example, I'm going to keep my R1 constant and just modify R2 so that I don't disturb my reference current of 1 milliamp. But let's say that I wanted to reduce my current through R2 by half. So instead of 1 milliamp through in my output current, I wanted to have half a milliamp. Then I will need to increase, so always go in the opposite direction. Because remember, I out over I ref equals to R1 over R2. So if I want to increase I out, I will decrease R2. If I want to decrease I out, I will increase R2. So let's go ahead and put 2 kilo ohms. So I'll double my resistor in order to decrease my current by half. And I can do that. And we can see my text has disappeared, but we can see that I'm now sitting at the half milliamp. So if I put this back to 1K, I go back to my previous value. So that's it for the emitter-degenerated current mirror. Thank you. Hello. Let's take a look at the Widlar current source next. And it's basically a special case of the emitter-degenerated current source where we have eliminated resistor R1 or have made R1 equal to 0. The advantage of this current source, we saw that it is the ability to generate a small current in the range of microamps without using excessively large resistor values. So for a basic mirror, for example, if we wanted to generate a current in the range of 10 microamps, we will need to use a resistor value of 900 kilo ohms, so close to 1 mega ohm. And in the Widlar current source, we're able to generate the same output current with much smaller resistor values, so none of them exceed tens of kilo ohms. Let's go ahead and do the calculations first. Let's imagine just as before, I want my source to be 10 volts. I'm going to assume my early voltage to be 100 volts, my beta value for the transistors to be 100. And let's say I choose my IREF to be 1 milliamp. And I want to design my source for an output current of 10 microamps. My reference current is going to be determined by my R resistor, so it's going to be VCC minus 1 VBE drop across Q1 divided by R, and therefore my R resistor is going to be VCC minus VBE divided by IREF, or 10 minus 0.7 divided by 1 milli, which is 9.3K. My RE resistor, I can calculate from the equation that gives me the relationship between I out and I ref. I'm not going to do the derivation again because we've already done it in a previous video, but we had seen that it was I out times RE is equal to the thermal voltage VT times the natural log of I ref divided by I out. So I can solve for I out, or excuse me, for RE, I want I out to be 10 microamps. I want to calculate that RE. That's going to be VT divided by I out, natural log of I ref over I out, or 25 millivolts divided by 10 microamps, natural log of 1 milli divided by 10 micro. And that gives me 11.5 kilo ohms. And again, I'm expecting my output resistance. In this case, to have the same form as the emitter-degenerated current source. So little r 2 times 1 plus Gm of transistor 2 R pi 2 in parallel with the emitter resistor connected to transistor Q2. I can go ahead and calculate those numbers. So little r02 is going to be equal to the early voltage divided by the quiescent collector current, IC2, or 100 volts divided by approximately 10 microamps. So that will be 10 mega ohms. Gm2 will be the ratio of IC2 to the thermal voltage VT. So in this case will be 10 micro divided by 25 millivolts, or 0.0004 ohm to the minus 1. Our pi 2 is going to be beta times little e2, or beta divided by gm2, which will be 100 times Vt, which is 25 millivolts, divided by 10 microamps, which is 250 kilo ohms, and Re is just 11.5 kilo ohms. So if we enter those numbers, I get R out is equal to in the order of 30 mega ohms. So around 10 times better than the one we calculated for the emitter-degenerated mirror previously. Let's go ahead and run the simulation. And now I should get my reference current should still be 1 milliamp, which it is roughly 1 milliamp, but my collector current at the output, it's going to be something very small. We can zoom into it. Change my axis here so we can see it more clearly. It's around 10 microamps. I can view my grid. And I can go ahead and try to calculate my output resistance by using the cursors. It's going to be still the inverse of that slope. We can see right away, my compliant range there. I don't have as much of a voltage drop across area just because my current is very small. So it's better than the emitter-degenerated current source that we previously saw simply because of that. So I was putting my cursors. I'll go ahead and measure from 1 volt all the way to 1 volt. All the way to 10 volt. There we go. And we can see that we've improved it by an order of magnitude, because before we had something e to the minus 7, now we have something e to the minus 8. So that sounds about right. Let's go ahead and write it out here. My R out, again, will be 1 over the slope, or 1 over that number, 1.82 to the minus 8, which is around 30 mega ohms. So more or less in the order of magnitude of what we expected. Thank you. Let's take a look now at the Wilson current mirror, and it resembles very much the base-compensated current mirror, except now we have moved Q3, so it is actually in series with the output transistor Q2, and we've also switched our diode connected transistor from Q1 to Q2. We're expecting that it's going to have a very good current transfer ratio, so I out will be approximately equal to Iref. And one of the major improvements of the Wilson current mirror over the basic mirror is going to be the output resistance at the expense of the compliance range, since we now have 2 transistors at the output that we need to keep out of saturation. Let's go ahead and do the calculations. If I wanted my Iref to be 1 milliamp, then I have, by Ohm's law, Iref is going to be equal to VCC minus, and this is now 2 voltage drops, 2 VBE drops, VBE, and another VBE from here to there. So VCC minus 2 VBE is the voltage drop across resistor R divided by R. And my R is then VCC minus 2 VBE divided by Iref, or 10 minus 1.4 divided by 1 milli, or 8.6 kilo ohms. my output resistance. For the Wilson mirror, we had seen that it approximated beta times R-out halves, obviously R-out for transistor Q2, even though they're all going to have a very similar R-out. Or actually, in this case, they will be for transistor Q3. But again, they're all going to have a very similar R-out, so I'm just going to express it as R-out. And so I'm expecting it to be my little rho. It's going to be the early voltage divided by the quiescent collector current, so 100 volts divided by 1 milliamp, around 100 kilo ohms, divided by half is going to be around 50 kilo ohms. This is going to be around 100 times 50K, or in the order of 5 mega ohms. So let's go ahead and run our simulation and see what we get. We can see again that we have suffered in terms of compliance range with respect to transistor Q1, or sorry, with the basic mirror. And go ahead and take a look at, first I'm going to add my grid, and now we're going to take a look at the cursors to determine the output resistance. My cursor one, I'm going to put in, I think, 1 volt. It is sitting there at 1 milliamp, so I think I'm going to put it at 1 volt, and then the other one is doing the same thing. Let's get off the first cursor. 1 volt. It's sitting at 5. Go ahead and close this, see if I can reset it somehow. So first one, 1 volt. Second one, let's show that. Now it's going. So second cursor at 10 volts, first cursor at 1 volt. And I can see my slope is 2.136 e to the minus 7. So I can write my R out can be equal to 1 over that slope. So 1 over 2.136 e to the minus 7, which is 4.7 mega ohms. And there we have it. An improvement in the output resistance at the expense of compliance range. Thank you. Hello, and finally we get to the Cascode current mirror, which consists of 4 transistors connected in a Cascode configuration. And we can calculate the value of our resistor to set the reference current Iref to 1 milliamp. Iref is again going to be equal to VCC minus 2 VBE. The reason for that is because we have 1 VBE drop across transistor Q1, another VBE drop across transistor Q3. So that divided by R. Therefore, R is going to be equal to VCC minus 2 VBE divided by Iref, or 10 minus 1.4 volts divided by 1 milliamp. 8.6 kilo ohms again. And so I'm expecting that my output current will be approximately 1 milliamp, and my output resistance I'm expecting is going to be relatively high, or much higher than the basic current mirror. The basic current mirror is this little arrow. In this case, is approximately beta times little arrow, so 100 times better than the basic current mirror in this case. And I'm expecting my compliant range to be lower than the basic mirror because, again, I have here two transistors in series. They both need to be out of saturation, and so I'm going to need at least two VC saturation voltages at my output. So I'm going to lose some compliance range, but I'm going to win some output resistance. Let's go ahead and run the simulation. Collector current here. Again, close to 1 milliamp. We can see that in effect it has less compliance range than the basic mirror. And then I'm gonna add my grid and my cursors so that I can measure my output resistance. Cursor. At 1 volt. And my second cursor. Picking up the first cursor for some reason. So I think I'm just gonna go ahead and move it out of the way. And not sure where it's acting up with the cursors, but first cursor is there. Second cursor comes up online, but then this doesn't do anything. There we go. One cursor at 10 volts, the other cursor at 1 volt. And that's my slope. And 1 over that is my output resistance. So R out equals 1 over the slope, or 1 over 1.765. So I'm just going to write 77 into minus 7. And I get close to 5.8 mega ohms. Which is a little lower than perhaps the 10 mega ohms we were expecting, but it's still within range, and certainly much better than the basic current mirror, and actually the best of the current mirrors we have seen so far for these characteristics. Considering it has, it has more transistor count, it has a single resistor, so it's a better design for integrated circuits than the emitter-degenerated mirror. And it does suffer a little bit from compliance range, but again, not as much as the emitter-degenerated mirror. So overall, if what you're looking for is a current source with a high output resistance, the Cascode or the Wilson, but the Cascode will be slightly higher, will be good choices. Thank you.